without further ado, okay, here we go. So I always like to start with an example, right? So given that I live in Germany now, I thought the Brandenburger Tor is a nice example. So please hold this image in mind. Okay, and now I take it away. It's not on the screen anymore. And then after a short delay, I will show you another image. And then I ask you, is it the same or different image? And hopefully, you know, everybody here has been able to do this task. And you can say, okay, it's the same image. It's the Brandenburger Tor. So you did this task and you were able to do it. And in doing so, you were probably using your visual system. So the visual system is a really nicely characterized part of the brain that we know a lot about. And so I like using visual stimuli and visual tasks and visual memory tasks in particular to study questions about visual working memory more generally. Okay. However, right? So I just told you that you were remembering this Brandenburger Tor and you were using your primary visual cortex to do so. But you may ask yourself, is that really what the primary storage site is for visual working memories? And should I just believe you when you say that? And of course, the answer is no, because there's been a lot of work and research on visual working memory, and especially early work when they listened to single neurons in the monkey brain, has showed that there's sustained firing and spiking in prefrontal cortices while a monkey is doing a memory task, such as remembering the Brandenburger Tor. Maybe not exactly that picture, but some kind of other picture. So there has, of course, been more work on that. And there they showed that, oh, actually, you can find sustained firing also in temporal cortex and in parietal cortex as well. And there's been additional work, again, in monkeys and monkey physiology, showing that maybe also sensory cortex has some sustained firing in certain tasks for memory stimuli. And now, of course, I'm really going and exaggerating here a little bit, because actually, when you look at fMRI studies, you see the same kind of results, and people find information or differences in activity during memory delays in sensory cortices and frontal cortices, parietal cortices, and kind of all over the brain. I don't know why, but my mouse keeps not working. Sorry. All right. So the question, is visual cortex really a critical memory storage site? It can be kind of converted into, well, is there really any one area in the brain that is a critical storage site? And this has often been the way that people have approached these kinds of questions. But lately, we've been kind of rethinking if this is really the way to go about it. And so in a really nice invited commentary with Polina Iamshinina, we've really tackled this question and came to the conclusion that this is probably the wrong question to be asking, because working memory is really this flexible mental workspace. And what it's used for is to have a behavioral output. Ultimately, you know, the behavioral output might really be what is determining visual working memory and how it works in the first place. So if you want to zone out and forget everything else that I'm going to say today, I think this is the really the big main point that ties everything together, is that this question of where is memory in the brain, I think we can move away from that. And what we want to maybe move towards is, okay, what is the behavioral requirement? And that is going to be what's driving working memory and how it's implemented in the brain. All right, so we argue that instead, while working memory is quite distributed, has some redundancy, right, is represented in several parts of the brain, maybe in different ways, and this is all done to ensure robustness as well as flexibility. These are critical things in support of behavior. All right, so today I'll talk about this in 4 different points. And I'll start by briefly repeating some of the work that we did in 2019, showing visual perception and memory representations in visual cortex. So I think this is a nice place to start. It's kind of a background for this work. And here the main point is that for adequate behavioral functioning, as I already said, working memory must be robustly maintained. So more specifically, let's say you're back in Berlin looking for the Brandenburger Tor. You have a memory of the Brandenburger Tor, And now you have to match this memory with the visual surroundings. Of course, if any kind of visual input would wipe out this memory of the Brandenburger Tor, you would be in big trouble and you would never be able to find it. So that's part of what I mean with visual memory must be robust. So in this case, robust against concurrent visual inputs. All right, so to study this, we put subjects in an fMRI scanner and measured bold activity in the visual cortex of their brain. And at the same time, they were doing this task. So in this particular task, they get a cue, and the cue lets them know what's going to happen during the delay. Then they get a brief target, 500 milliseconds, and then there's a 13-second delay. And after the delay, they rotate this bar by pressing some buttons, and they want to match the orientation that they're remembering. Now, what happens during the delay is that there's a distractor stimulus on the screen for 11 seconds. And in this example, this is a Fourier filtered noise stimulus, and it's phase reversing. And it does that for 11 seconds. Now, there's a second condition where during the delay, another oriented grading is presented, and it's also phase reversing, also for 11 seconds. And then there's a third condition where nothing is shown during the delay. So in this condition, we want to replicate a lot of previous work where people have shown that you can see information about what's being remembered during the delay. And in most of those delays, there was no visual input. So this condition is really should work, right? This is kind of our ground truth. All right. So we scanned 6 subjects for this. What's really important to note here is the target orientation was random, and the distractor orientation in the grading distractor condition was also random. And those two were completely independent of one another. The subjects completed 108 trials per condition, so in each of these 3 conditions, and they did this over the course of 3 different days, so they were in the scanner 3 different times, and we measured their whole brain. Then there was another task that they did in the scanner where they would see physically a grading. It would also phase reverse, I think, for 5 seconds, and they were doing an orthogonal task. So what they were doing with this grading, sometimes it would dim a little bit, and that to indicate when there was a dimming. So they were paying attention to the stimulus, but they were not doing an orientation task. All right, so first of all, I was already saying that visual working memory has to be robust against interference. And in this paradigm, we see indeed that irrespective of there being a noise or a grading distractor, for 11 seconds during the delay, the behavioral error is really not affected at all by this kind of disrupting input. Secondly, were these distractors driving visual responses? The answer for that, at least I'm showing this for V1 here, is yes. Particularly this Fourier filtered noise distractor was driving a very robust bold response, the grading distractor as well. And this is the sort of control condition in this case, right, where there was no distractor shown during the delay. And just to orient you to this plot, this little sliver of gray here is when the target was on the screen. Then this bigger gray box here is when the distractor was on the screen. And the last gray box is the period during which subjects were rotating the response dial. All right. So beyond univariate analysis, what we wanted to do was some multivariate analysis. So we wanted to decode the orientation that subjects were remembering. So because we used random orientations, on trial 1, let's say the orientation could be 79 degrees. On trial 2, it could be 42 degrees, trial 3, trial 4, et cetera, et cetera. Now, one way to do decoding in this kind of paradigm where you have random orientations is just to say, okay, we take a decoder, for example, an 8-way decoder, and we're going to decode where this orientation was. So let's say you have an orientation of 42 degrees, and then on another trial, you have an orientation of 131 degrees. You would say those are in different bins, and that's what you want your decoder to distinguish. However, there's a little problem here is that orientation space is continuous. And so when you have 42 degrees versus 50 degrees, the decoder thinks that's kind of the same. They're in different bins. They should be different. But in truth, these are very similar and they're on the edge of the bin, and subjects may not even be able to tell the difference between them, right? So the question is, what is actually a better way to discretize a circular space? And in the past, what people have done during the experimental design, they would do something like this. They say, okay, we show an orientation that's either 45 degrees plus or minus something, right? And they do, let's say, delayed match the sample task, or 135. And then we just ask the decoder, okay, was it this orientation or this orientation? And they're quite different. And the decoder is quite good at that. We cannot do that with random continuous orientations, but we can do something similar. So what we ended up doing is saying, okay, well, we have orientations that are roughly 45 degrees, like in a bin around 45 degrees, and we have orientations that are in a bin around 135 degrees. And so what we end up with is, again, a binary decoder that's classifying 45 against 135 degrees. Of course, we have some orientations left now that don't fall in those bins, but we can make more bins. In this case, we can make a vertical and a horizontal bin. So now we're decoding 90 versus 180 degrees. So we have these two decoders, an oblique, if you will, decoder and a cardinal decoder. And then if we want to calculate the decoding accuracy, what we do is we take the average of these two-way decoders. And that way we don't have a problem with binning, continuous data, etc. All right. So when we do this for the memory trials, and for the memory orientation, so now we want to know, okay, during the delay, which orientation were subjects remembering? We do that for several areas along the visual hierarchy. So starting from V1 over here and going up to IPS over there, we see that we are able to decode the orientation that's being held in memory really well. And also there's really no differences between the three conditions. So irrespective of distractors, what we showed here is that we can decode the orientation that subjects are remembering. So really what we're doing now, right, we're showing this target. Once it's held in mind, we can decode what is being held in mind. But there's, of course, this other condition, 1 out of 3 trials, there is a distractor shown, which is also an orientation, and we can decode it as well. So now we are talking about the sensory representation, so something that subjects are actively viewing. And that's shown here in gray bars. And the main point here is that you can decode that as well, which you would expect, right? Because this is coming in from the eyes, it's entering visual cortex, and now this information is there. All right, so the take-home message here is that V1 seems to have this capacity for region-wide multiplexing of both sensory and memory data, and not just V1, right? We see this kind of throughout the visual hierarchy. And this is a little bit of the background for the things that I want to talk about next. Because one of the cool things of the paper is that we saw different kinds of representations, and I'll unpack that a little bit more. So everything I've shown you so far, what we've done is we trained a model on sensory data. So on this independent mapping data, when subjects are actually actively viewing stimulus, and then we train the model, we test the model on the memory data. So what we see now is that there's a generalization from however activity looks like, right, when you have visual inputs, to what that activity looks like when something is being held in memory. And this worked in early visual cortex, but it didn't work in area IPS. And that's somewhat odd, was when you compare it with some other work, they showed opposite patterns, namely that actually in V1, they were not able to decode when there were also distractors shown, whereas in IPS, they were able to decode. But they did something slightly different. They had a different analysis approach. So first of all, just to show you for IPS what this actually looks like, this is what, I'm using a different y-axis now, but it's equivalent. This is what the amount of information looks like in IPS about things that you're holding in memory when you're training on independent sensory data. So there's really not much there. All right. So of course, memories may be represented in the same way as sensory inputs, but they may also be represented quite differently. So if we want to know something about non-sensory like representations, what we can do is we can actually train on the memory delay data and then also test on the memory delay data. And then we're not putting any constraints on what we are able to find. We are able to find any kind of memory related representation. So I'll just cheat and say that this works for visual cortex, perhaps for uninteresting reasons. But the question, of course, is does it work for area IPS? And it turns out, of course, that it does work. Otherwise, I wouldn't be telling you this story. So now when we train on data from the memory delay, you actually see that area IPS has really robust responses and has a lot of information about what's being held in memory. All right. So what the main point is here is that there are several loci and several codes that are being used. So on the one hand, we have, let's say, a high dimensional code, which is very vision-like. It's maybe some kind of pixel by pixel retinotopic map-like representation. And we see that in B1 and other early visual areas. There might be a second code that's somehow transformed away from the sensory-like code, maybe lower dimensional. It could be, let's say, Cartesian coordinate or a vector or any kind of representation, right? We don't really know. And we see that this kind of format is there in area IPS. So the question now becomes, are there higher levels of abstraction outside of early sensory cortex? So we see that there's multiple and concurrent levels of abstraction, but we want to know a little bit more about what is this abstraction and how is it defined? And also just a kind of a side point that I want to make here, it really matters how you train your model. So now we train on either an independent localizer, which is sensor driven, or we train on memory delay data, and we get quite different results. And this is something that we have in our paper as well. So I would definitely recommend it. Okay. So again, we know that these codes are different, but we don't really know what they are. And so that's some of the work that we've been doing over the past couple of months, looking at veridical versus categorical formats for memory information. And again, like what I was saying is here we really want to know what is the format, right? Because we know that in IPS it's not sensory driven, but what is it then? And also, do these codes now really differ from sensory codes? And if so, how do they differ? So really kind of doing something a little bit more specific. And so the tool we use for that is called representational similarity analysis. And so I'll quickly go over that. So let's say you have a bunch of stimuli, in this case, some faces and some gazebos, and you measure them several times in the brain. You might expect that there's a high degree of similarity between one face and the same face shown at a different moment. There may also be quite some similarity between that face and a face that's much like it, but it may not be very similar to gazebo images. So all the faces might be quite similar, and they will be quite dissimilar from gazebo images. Of course, the gazebo images are similar to themselves. And when you have this kind of structure and you do this kind of analysis, you can compare this with different kind of models. So in this case, you can say, well, maybe one hypothesis we have is that images are only similar to themselves, but not similar at all to any other images. Or the second hypothesis, which is what the data in this case, it's fake data, right? But looks like most, is that, well, maybe all face images are quite similar and all gazebo images are quite similar, but they're dissimilar from one another. All right, so what did we do? We used the same data from the same experiment that I showed you before. So we have a bunch of trials where subjects are either seeing or remembering a bunch of orientations. And then we measure from a visual ROI, such as B1, B2, etc. And we get this N by N voxel matrix. So a number of trials by number of voxels. And I just want to highlight that this whole analysis approach and idea is from Chaipa Chunhras, who is like one of the most amazing people I've ever worked with. He always has really great ideas and he just like codes this stuff up. So he really credit where credit's due. He did the following. So first, because we had, again, these random orientations, he decided to put the orientations in several bins because otherwise we don't have a lot of trials. So he decided to chop this orientation space up in 16 bins and each bin spans 11.25 degrees. Then what we do is we take this trial by voxel matrix and take one trial out. And so this one trial will be a test trial and the remaining trials will be training data. So what do we do during that training and testing? So first of all, we take for each bin, so now we have 16 orientation bins, the mean activity across all voxels. across all trials. And then we compare that to the left out trial, which is a test trial. And we compare that by computing a normalized Euclidean distance, but you can do this with a correlation as well. All that it will tell you is how similar your test trial is to the different bins. And so I can show you what that looks like. So let's say on trial 1, you have your trial 1 left out. You compare it to the mean of bin 1, it's quite similar. It's a little bit less similar to the mean of bin 2, so these orientation bins, etc. You do this for all 16 of your bins. Then you do this for your next trial, and you do this for all the trials in your experiment like this. And of course, now you have n trials, but you also need to bin those in your 16 bins. And so then in the end, what you end up with is this matrix, a similarity matrix, that shows you how similar each orientation is, either to itself and to the other orientations. All right, so now, of course, we want to have some hypothesis here. So how is orientation represented? So we started with a veridical model. And the idea here is as follows. Let's say you have any kind of orientation in orientation space, let's say 42 degrees, then you would expect that orientation to be most similar to itself. If you compare that orientation to, let's say, 50 degrees, it would still be quite similar. But the further away you go in orientation space, the more dissimilar it becomes. So what you end up with is this sort of diagonal looking model, which we term the veridical model. Okay. Then we have a second model because our previous data led us to believe that there's some kind of abstraction happening in IPS, but we don't know what. So we had to come up with a hypothesis. And we based this hypothesis on what we know about cardinal axes. So we know that there is something called the oblique effect, which means that people have much higher discernibility at cardinal axes compared to oblique axis. So if you have to tell two orientations apart, that are either close to vertical or close to horizontal, you're really good. If you have to do that same task for orientations around the obliques, you're much worse. So that's one way in which we know orientation space is actually not quite equal. Not all orientations are equal. And then there's another phenomenon where you ask people to replicate, or let's say respond. So you give them an orientation, you say, now show me what that orientation was by rotating one of those dials. And what you see is that people really exaggerate the tilt of orientations away from these cardinal axes. So the idea is that, let's say I show you an orientation of 2 degrees, you might reply and say it was 7 or 8 or 9 degrees, right? So the idea here is that we thought these cardinal axes really, really matter. And maybe all that people are doing when they're having some kind of abstract representation, they are classifying where an orientation is relative to those cardinal axes because they are so important. So again, let's take this orientation of 42 degrees. If you show someone that orientation, all that they might be doing for any other orientation is saying, okay, where in which quadrant is this, right? So any orientation within that quadrant will look similar to an orientation that's 42 degrees, because really all that matters is where it is relative to cardinal. And so what you would see then is that the other quadrant, the other side of a cardinal, will be dissimilar in this case to this 42 degree orientation because it's coded in another part of this space. All right. So how is orientation represented? We have these two competing models now, a veridical versus categorical model. And all that Chaipat did was basically make a mixture model, right? Say, how much of each is there when we look at our data? So we get 2 beta weights out, one for the veridical model and one for the categorical model. So the first thing we wanted to look at is, okay, we have this independent mapping data where subjects are just looking at this orientation that's being presented. What does this look like when we do this RSA analysis? And the data look like this. So what you see is that there's quite a strong diagonal, you see that there is some changes along the visual hierarchy. But of course, we want to quantify this. So we fit this veridical versus this categorical, this veridical and this categorical model to this. And so first we look at the veridical model. And on the y-axis here is the weight, by the way. And we look at the categorical model. And so what we conclude when we compare our models to this data is that viewed orientation representations They are veridical-like, right? They are represented in this way that we would hypothesize, but not categorical. So that really doesn't fit here very well. Now, the second thing, of course, we wanted to do is look at these remembered orientation representations. So again, now here's the data. You can already see it looks quite different from what we saw in the viewed orientation situation. So now when orientations are remembered, we want to see how well these two models fit the data. And what we see is when we look at the veridical model, also this works quite well. So even these remembered orientations have this component that is veridical, so continuous along the orientation space. But now when we also look at the categorical model, what you see is there is indeed also a categorical component to these representations. And you see that this increases somewhat as you go up the visual hierarchy all the way to IPS 0, and then later on things look a little bit different. All right, so the overarching conclusion here is that as soon as these inputs disappear, now you have an orientation that you have to hold in mind. Its representation becomes more categorical, and you see this more strongly also as you go up the visual hierarchy. All right. Then as a final thing for today, I want to talk about really flexibility of visual working memory, because people kind of take this for granted and they often write this and say this, but it's not often been shown, and certainly not in a single task. So here, the really big take-home point again is that visual working memory is there in service of behavior, and therefore it must be flexible. Can we really show this? So imagine again, you're walking to the Brandenburger Tor. And the question now is, how does the brain actually support visual spatial working memory while you're doing this real life task? And I want to highlight that this is the work from Maggie Henderson. She did all the heavy lifting on the analysis and the scanning, etc. And she came up with this really nice way to kind of conceptualize this. Is that one, if you're on your way to the Brandenburger Tor, you may just remember all the landmarks and have images in your mind of the landmarks and how you have to go there in a visual manner. But there is, of course, an alternative strategy that you might employ. So you might have this idea that you start at a certain point, and then you have a series of motor movements. So you turn left, you turn right again. So you can have either a very visual way of doing this task, but you can also have something that's more of a motor strategy here. So what we did is we took a very classic visual spatial working memory task. So subjects are shown a dot target. So it can be anywhere along an invisible ring. And then they have to remember that target over a delay. But now what we do is we have two different strategies that we try to encourage for our subjects: a retrospective and a prospective memory strategy. So I'll start by explaining one of the two first. So you see this target, you have to remember its location, and then you get a short cue for 2 seconds that tells you which of one of two conditions you are in. Next, you get this preview disk. And what this preview disk tells you is something about the response. So each color of this disk corresponds with a finger response. So in this case, let's say light gray corresponds to pressing a right button, dark gray corresponds to pressing a left button. And you can kind of imagine where this dot was. And then you can also kind of know which response you will have to give after the delay. So now there's a 12-second delay. And in this particular condition, there is another disk, but it's set exactly identical to the preview disk. So your response disk and your preview disk are the same. So you already know which button you have to press. And we call this the informative condition. So in this condition, you can use a prospective memory strategy, because as soon as you've seen the preview disk, you can sort of project out what you will have to do in the future. And all you have to remember is something about a future action. Now we contrast this with an uninformative condition. Here the preview disk might look exactly the same, but now you know you're in a different condition and that this preview disk is not at all indicative of what will happen during the response period. And so during the response period, you might see this disk, and in this particular trial, now your memory target actually falls on the dark side of this disk, and you would have to press another button. And so we call this our retrospective condition. So here you have to rely on the information about the target and where it was in space, in visual space, in order to do this task at the end of the delay. So we again scanned 6 subjects. Importantly, again, that this target location is random, but so is the orientation of the preview disk. Subjects completed 200 trials per condition, and we did this over 2 scan sessions, and again, scanned the whole brain. So first of all, I wanted to show you this behavior. Well, and what this shows is that subjects indeed use this preview disk to their advantage. So they weren't just ignoring it and doing the same kind of strategy in both conditions. They were really using this preview disk. So if they knew what their response would be, they were more accurate. They were also faster towards the end of the trial. So I also want to just quickly show you the univariate responses here in area V1. And what we show here is that there's really not much in terms of elevated bold in the early sensory cortex during the delay, and this replicates much previous work, which also often is unable to find elevated bold responses during the delay. Then when we move a little bit more anterior to area IPS, what we see is that there is actually higher bold response when you cannot pre-plan. So in this case, this is in the uninformative condition. And again, this replicates previous work doing this kind of paradigm. Then we also looked in motor cortex. So we looked in S1, M1, and premotor cortex, and I'm just showing you M1 here. And what we see here is that there's a slight elevation early during the delay, where you see that when there is information in the preview disk, there is a slightly higher univariate response. Okay, and so I don't have to explain this very much at this point, because I already explained it before, but it's slightly different because now we're talking about 360 degrees instead of 180 for orientation. But we can have dots somewhere along here or dots somewhere along here, and they should be quite different. So what we end up with is actually decoding accuracy using, again, 2-way decoders, but now we have 4 of them, and we take the average of them when we look at accuracy. Okay. So what does this look like? Here on the x-axis, you'll see there are quite a few more areas. So we have early visual areas, we have IPS, and then we also have these motor areas. And the data I will show you here, I just want to be specific about this. We trained our model on spatial working memory data, actually an independent spatial working memory task that subjects were doing. And when we look at the informative condition, even though subjects kind of know beforehand, right, what their motor response could be, which button they will have to press, you still see that there's quite some decoding in early visual cortex. But when we compare that to the uninformative condition, where subjects cannot pre-plan their response, you see that there's much more information in early visual cortex compared to in the condition where they do already know their button press. So especially these early visual areas, you see that there's these nice differences. So you can decode in both conditions, but much better when they have to use retrospective memories. Then in IPS, again, in the uninformative condition, you can still decode, but no longer in the informative condition. And when we see, when we move to motor cortex, there's just no visual spatial information here. But of course, there's also the button press. So subjects have to use either their left or their right finger. So what we can also do is now train a decoder on this output. So are they using a left or a right button press? And when we do this, and we train again on the memory delay period, so when subjects are remembering, and in this case, we do a leave one trial out cross-validation. What we see is that now there is actually in motor cortex quite some information during the memory delay about the upcoming button press, so this prospective memory representation. And if we look at the uninformative condition, there is no information at all about which button press is upcoming. All right, so again, I want to just highlight this result in motor cortex where we see this prospective memory for button press. Okay, and this is again just to summarize. So we see this retrospective spatial working memory information in visual cortex, while we see this prospective button press memory information in motor cortex. And so what that looks like is kind of like this. We have a situation in which we don't know which button we have to press. Then we use visual information or visual cortex to represent this sort of vision-like stimulus. Whereas if you do know which button you have to press beforehand, you then use a different cortical locus and probably a different kind of code to now represent this prospective memory. Secondly, I want to show you this, which I think is very cool. So is there an information handoff? So we can look at this over time in a trial. So here, this first gray bar is when the preview disk is presented to the subject, and the second gray bar is when the response disk is presented to the subject. And what you see is that roughly here, after let's say 7 seconds, there is a divergence. So if they don't know which response they have to give towards the end, then this information sort of stays sustained throughout the delay. But if they do know which button they'll have to press, you see that indeed there's information that goes down. And then if we look in motor area M1, now we look at this motor response decoding, you see that this is exactly flipped. So after this preview disk, if they know which button they have to press, you see that this information about the prospective memory goes up and stays up and sustained throughout the delay. All right, so these memory codes can be flexibly reformatted based on these behavioral requirements in the same task. Okay, so I already talked a little bit about, but what are these codes? So I can kind of do this for this data as well. So far, everything I showed you is now trained and tested on a memory delay data. But that doesn't really tell us what kind of code or what kind of format the brain is using. But we can again look at sensory-like representational formats by using a sensory localizer now to say, okay, if I have this checkerboard here, and how is that evoking certain voxel patterns? And then do those generalize to the memory data, because that will give us a grasp of whether or not this is sensory-like or similar to a sensory-driven response. Similarly, we can do that for motor presses as well. So we can have subjects actively press with their left or right finger and see if patterns of activation now look similar to what we see during the memory delay. And so I'm just gonna quickly say, yes, this works. So when we train on either active sensory inputs or active motor presses, it looks like there's generalization from those model training data to what's happening during the delay. So this gives us an idea about the format of the mnemonic codes. And so we can say that actually what the brain is using is something that is either sensory-like or motor-like. All right, and so what do all these things together end up telling us? And again, I really hope that this is clear by now, but that the way we are thinking about working memory at the moment is that it's really this central resource in service of behavior. And so whatever the behavioral requirements are, that is what working memory will be, and that's how it will be coded. That's where it will be coded in the brain. And it's really quite flexible. So we should start from behavior and then sort of reverse engineer our way back into what working memory representations really are. All right, that is it. So I want to thank, of course, Chaipat, Maggie, and John Francis as well. So all of these data came out of his lab. And I'm happy to answer any questions.